Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And let's just do a quick recap of what we have talked about so far. So in terms of sequences, we said that sequences are essentially functions, and but they are on a discrete axis. So their variable is a discrete integer. And in terms of Java, the integer could be int variable or long variable, okay? And then, so it's basically a function, but we usually don't denote a discrete function, f of some discrete variable with f of n. We typically denote it by some a, b, or anything, some symbol or a variable with a subscript of n, okay? And again, the an, the value of this function, can be real or complex. Here I'm going to focus on the real numbers, so the function is real, and the index can be negative, 0, or positive. We typically look into the cases where the index starts from 0 and is positive, or it starts from 1. These are two mostly used cases, all right? So one example is 1 over n squared. This is a sequence, and then we said that there are typically two families of sequences that have a unique behavior. One is monotonically increasing, which means increasing the n will result in a strictly increasing behavior for the sequence, and just increasing means the next term can be greater than or equal. And monotonically decreasing means that the inverse of this statement. So each term, as we increase n, each term gets strictly smaller and smaller. And just decreasing means it can be equal or less than the previous terms. All right. And then we said that for the limit of a sequence, the definition is that what happens to the sequence as n goes to infinity. And we just calculate this using the rules of the limits. It has a formal mathematical definition, but here, for example, 1 over n squared, when n goes to infinity, obviously goes to 0. And then the limit of 1 plus 1 over n to the power of n, when n goes to infinity, the base goes to 1, but the power goes to, but it always stays above 1. So anything slightly above 1, when you raise it to infinite power, it should give you infinity. But because the base is approaching 1, these two kind of cancel each other out. And the key here is that they cancel each other out at the same rate. Therefore, this limit exists, and it's just the Neper number or the natural number, E, all right? Or sometimes this is also called Euler's number. So Euler's number. And we said that in terms of sequence, the best way to implement it in Java is using a functional interface, because then we can pass it as lambda expressions, and it's a very convenient way to do it. And then we said that we can do recursion for sequences. A lot of times we define a sequence based on a recursion, and it could be a simple or linear recursion, which means that all the coefficients are constant numbers. For example, Fibonacci, an equals an minus 1 plus an minus 2. Geometric sequence, an is some constant number times the previous one. But there are some non-linear recursions where the coefficients actually depend on the index. For example, factorial an is n times n minus 1. So this coefficient is changing each time we calculate a term. And then we said that for recursion, obviously we need the initial conditions so that we can start from the initial terms and then evaluate the next terms. And based on how many recursive terms we have, we need those many initial conditions. For example, Fibonacci has 2 recursive terms, so it requires 2 initial conditions. Geometric sequence has 1 recursive term, so we only need 1 initial condition. And these recursive sequences can in fact have closed form solutions, and it's always best to calculate the sequence based on their closed form solutions. It's much easier to program it using recursion, but recursion is always not the best case, because In Java, you have the method stack, and then going into the stack deeper and deeper, and then have to coming back. It just adds a lot of overhead in terms of computation. All right, but there are ways to mitigate that. One of them is memoization, and you can just look it up. Memoization is a great way of increasing the performance of the recursive calculations. For example, one famous example is just Fibonacci. So if you just look it up, you can see how memoization works for recursive sequences. And then we said that most of the times engineers and physicists deal with a particular type of sequence, which is basically the sum of the terms of another sequence, and we call that a series. So a series is basically, or the partial sum of a series is when you sum another sequence from some fixed index, which is typically 0 or 1, to some n, and this n is the variable. Okay, so let's say k is 0 here or 1. I from 0 to n of ai is sn. All right, so we sum over this sequence a and get another sequence. And in fact, this is some sort of sequence transformation. And what happens is that you take a sequence, do some operation, algebraic operation on it, and then you create another sequence. That's called the sequence transformation. And series is one way of sequence transformation. And we said that caching or memoization helps with increasing the performance of calculating. And what it means is that let's say I calculate S0, S1, S2. If I want to calculate S3, instead of calculating all the terms of A, I can save S2 and just add term 3, and then calculate A at 3, and then add it to the previous term. I don't need to, if I want to calculate S1000, if I have already calculated S999, then I can just use that value and add it to 8000. All right, this is again memoization or caching. And then we said that okay, this partial sum is another sequence, so we can ask what is its limit, and the limit of this partial sum is called a series. So series is the limit of a sequence, which is generated by summing another sequence over some finite number of terms. All right, and then the limit exists if the difference between two consecutive terms gets smaller and smaller as n gets bigger and bigger. And then the necessary condition is that in order for the series to converge, or in order for the limit of this partial sum to exist, this sequence A must have a limit of 0. If it has a limit anything other than 0, the series doesn't converge. So that's a necessary condition. And then we said that numerically we can try to implement some convergence tests, because we cannot sum over infinite numbers of terms. Okay, so test for convergence, we discussed this. We can define the convergence in terms of an absolute error or absolute error for the sequence, because most of the time, or almost all the time, you don't know the exact value of the limit. So you have to you have to define your error based on the behavior of the sequence, right? This is what you have. And then you can also define a relative error, and then look at the speed of convergence. All right. One of the very famous series that we talked about was Taylor series, and we implemented that in Java, and we said that Taylor series requires the calculation of the derivative of f many times. Each term n of the sequence requires the nth derivative, and then we discuss how to do that. But then here's the new topic, which is called convergence acceleration. And the idea for convergence acceleration is that most of the time, if you have a series and you just want to, if you have a sequence and you want to find its limit, the sequence has a very slow convergence, which means if you want to get a good approximation for the limit of the sequence, you have to evaluate the sequence at a very large number. And that sometimes is not a good idea, especially when you're dealing with series, because if this series has a very slow convergence, I have to let's say evaluate it at n equals 1 million. That means I have to add 1 million terms of this sequence together, which is not a good idea. All right, so somehow we want to increase the rate of convergence of this sequence, which means we want to get the same accuracy but adding summing less and less numbers of the terms of this sequence. And typically the way we do it is we define a sequence transformation, and by that first we have to define what is the accelerated convergence. So consider that we have a series an that converges to A, and then consider that we apply a transformation to this an series and create another actually this has to be a sequence an that converges to A, and then we construct from this initial sequence an a new sequence bn that also converges to A, but has the property that the limit of bn minus A divided by an minus A n goes to infinity is 0. Okay, if this condition is met, then we say that bn has a faster convergence rate than an. If this is any number but 0, then we say that bn and an have the same convergence rate. If the limit is defined such that bn minus A divided by an minus A to some power, let's say power of 2, is 0, we say that the convergence of B is quadratic when compared to A. All right, so if this number is not 0, bn and an have the same convergence rate, and that transformation that we used doesn't do anything better. But if this limit becomes 0, this sequence bn converges to the same limit as A but with a faster convergence rate. Now let's look at one example. So let's say bn, one example is bn equals, for example, half times an plus 1. Let's just format this correctly. All right, so this is one example. And in this example, what you see is that basically if A converges to capital A, then the limit of this is half times A plus A, which is A. So Bn also converges to A. So if An converges to A, Bn also guaranteed to converge to the same number. But if we calculate this limit, Bn minus A divided by An minus A, we see that what happens here is that this number is because when n goes to infinity, an plus 1 and an are pretty much the same, right? Because n is very large, or n is much larger than 1. So bn becomes just half times an plus an, which is an. And this limit becomes 1, right? This number becomes 1. That means that this transformation of sequence of an into bn has a linear or has the same convergence rate. So it's not useful to do this transformation. It just has the same convergence rate as A. So it doesn't help at all, right? Now, most of the time we do the transformation on a sequence because we are calculating a series of that sequence. So here, this is from Wikipedia, and it's the series acceleration. And it says, in mathematics, series acceleration is one of a collection of sequence transformations. So we take the sequence and then transform it for improving the rate. So basically, this sequence is the partial sum sequence. So to remind you again, it's this Sn, right? We want to calculate the limit of this sequence, which is the series over this A sequence, right? We start with this, we create a new sequence, and then we want to calculate the limit. But most of the time, this sequence has a very slow convergence rate. So we are trying to find transformation to apply to this Sn, which is the partial sum of the series, to to accelerate the convergence, which means we want to calculate at a very smaller index for n and to get a good accuracy. All right, so it's a series sequence transformation for improving the rate of convergence of a series. So take note of these keywords. Techniques for series accelerations are often applied in numerical analysis where they are used to improve the speed of numerical integration. So that's one use case, because when we calculate numerically calculate an integral, we divide it into some sub-intervals, we create a series, and then let the n goes to infinity, right? So numerical integration is an example of a series, and we want to calculate the limit. Series acceleration techniques may also be used, for example, to obtain a variety of identities on special functions. Thus, the Euler transform applied to the hypergeometric series gives some of the classic well-known hypergeometric series identities. So Euler transform is one of the examples of the sequence transformations. Now here I have listed some of the famous or most commonly used transformations. And before looking at them, let's define two things. One is the difference of a sequence. We said that a sequence is a discrete version of a continuous function, right? And for continuous functions, we have something called derivative or differentiation. For sequences, we have a discrete analogy to that, and it's called a difference. Difference, let's use the symbol delta, and so the difference of an is an plus 1 minus an. So immediately you can see that this is some sort of transformation, because we can define another sequence bn, which is delta an. All right, and we can calculate that sequence at any n, right? So this gives rise to another sequence, which means that this delta is just a very simple transformation of the sequence. And most commonly, this difference is defined for a forward case, where delta an is an plus 1 minus an. But we can similarly define it for a reverse case or reverse difference. So the first one is called forward difference, the second one is called reverse difference, and let's show it by delta bar, which is an minus 1. Okay. Now, having that in mind, the binomial transformation takes a sequence an and creates a partial sum sequence Sn, which is defined from index 0 to n minus 1 to the k, the combination of k from n times ak. So remember, we're transforming an sequence into Sn sequence. All right. Euler transform takes an alternatively changing sign of a sequence that has also a factor of minus 1 to the n. So its sign changes alternatively and transforms into another sequence, minus 1 to the n Sn. All right. And the definition is this: if we are calculating the series over this minus 1 to the n an, we transform this sequence into minus 1 to the n delta na over 2 to the power of n plus 1. And this delta na, as I mentioned, this is another sequence. So we are calculating it at 0th, or the first term of the sequence. All right. And divided by 2 to the n plus 1. So you differentiate or calculate the difference of n times and find its basically first term, 0th term, or you can say that I calculate the difference of a0 n times. That's another way of looking at it. So this is another way, and these two are basically have the same limit, but this Euler transform version has a faster convergence rate. All right. And there are two famous nonlinear transformations which are very famous. The first one is Aitken transform, which is also called delta squared process. So for Aitken transform, just note that these Aitken and Shanks, these are nonlinear transformations. And the Aitken's delta squared process is something like this. Let's denote the sequence of xn by capital A. and then AX is the transformation of this sequence, which is another sequence. Let's call each term AX sub n. So AX sub n is xn plus 2 minus the difference, or the first difference of xn plus 1 squared divided by delta squared of xn. Now what is the continuous version of this? For a continuous function, it's like f of x minus f prime squared over f double prime, something like that. All right, so the first difference squared divided by delta squared, and delta squared means, as I mentioned again, delta an is the first difference, which is another sequence, right? Delta an. So you apply a delta over this new sequence, delta an. It becomes delta an. All right. And then this can simply written as this. The AXN is xn plus 2 minus xn plus 2 minus xn plus 1. So this is the first difference for xn plus 1 squared divided by xn plus 2 minus 2 xn plus 1 plus xn. What I want you to notice here is that calculating the Aitken transform of x at index n requires the knowledge, or requires the calculation of xn, xn plus 1, or xn plus 2. Okay. Now the next one is Shanks transform, and the idea here is that if I want to calculate a series from, let's say, 0 to infinity or 1 to infinity or any index to infinity of am, so small a is given, and let's say this series converges. So we already know that it's a convergent series, and let's say it converges to capital A. So we create a partial sum sequence from A. So basically this is our first transformation, going from AM to capital AN, right? We take this sequence and transform it into capital N using this partial sum. And now in order to so this sequence capital AN has, let's say, has a slow convergence rate. So we can define the Shanks transform on AN, and it's pretty much Aitken transform applied to AN minus 1. That's the same thing. So SAN is just AN plus 1 minus AN plus 1 minus AN, which is the first difference of AN squared, AN plus 1 minus 2AN plus AN minus 1. This basically is the Aitken transform applied to xn minus 1 or AN minus 1. All right. So in order to calculate the Shanks sequence, Shanks transform at index n, we need to know or calculate the A at n minus 1 and n plus 1. All right. So basically there's not much difference. But then the idea here is that once we are going to calculate the series of the small a using the partial sum sequence, we can apply Shanks transform as many times as we want. So we can apply Shanks to AN, it gives us another sequence, and then we can apply Shanks to this new sequence. So it's typically denoted by Shanks squared or S squared, which is S Shanks of AN, and S cubed is Shanks of Shanks. All right. So this is how. But then the question is, how do we implement this in Java? And the first approach, I think, is the best approach, and because we already defined a sequence as a functional interface. All right. So instead of defining a class to implement this transformation on this sequence, because remember, when we apply a transformation, one of these transformation to a sequence, the results should be also a sequence, right? For even a simple difference, when you apply it to the sequence, it's another sequence, and you calculate it at any given n, right? So we take our functional interface sequence object, and we want to keep it as a functional interface, but we want to apply new methods to calculate this transformation. And the way that Java allows that, to evolve an interface but keeping it again as a functional interface, because remember, functional interface must only have one abstract method, which is where we evaluate our sequence. So we use default methods. All right. Default methods allows us to add more methods, more capability to a sequence, basically evolving that interface without breaking the contract of the sequence being a functional interface. All right. So let's head to Eclipse, and I'll show you how I've implemented this. So In our sequence project, we had a sequence object, which is a functional interface, all right, and then a series class, which basically takes a sequence and then sums over some index that we provide from the initial index to the last index. And here I've changed the int types to line types because it just takes more memory, but it's better to have it as line, right, just to be safe. And then so this was the main idea, but we also implement something called caching. So we calculate the sequence at each point and put them in a map and then retrieve them at another time. All right, so let's not worry about caching at this point, but these are all two main classes. Now, in order to evolve this interface, we already have this functional interface. So this is our public abstract method, which is called evaluate, and takes a long variable k and basically calculates ak. So k goes to ak, all right? And again, we want to only have one public abstract method to be able to use it as a functional interface and use it as lambda expressions. So what I've done here, I've added a default method here called, and the return type is a sequence, because when I apply the difference, the difference is like a sequence transformation, right? The forward difference, and it has to return a new sequence, right? And the good thing here is that having this single public abstract method allows me to just write it as in a very convenient way using lambda expression. So when I calculate the difference, it creates a new sequence, and basically n goes to, I call the evaluate function at n plus 1 minus evaluate at n, right? Again, this is a lambda expression, which means the return type is automatically a sequence interface. Now what I could do, I could also call this over this method, the evaluate method, but it's not necessary. So this is how I transform a sequence using the difference. So difference is defined as a sequence transformer, and it returns a sequence. For Aitken, the same thing. So I add a new default method called Aitken, and the return type is a sequence, all right? And again, I use a lambda expression. So n, it takes the nth term of this current sequence and calculates it at n plus 2 minus, this is the first difference, n plus 2 minus n plus 1 squared divided by n plus 2. So this is delta squared, n plus 2 minus 2n plus 1 plus n. And I'm just calling the evaluate method, all right? And then for the Shanks transformation, I could just call the Aitken, and basically I could write something like this. So I could say return n goes to Aitken, or basically call the method Aitken at, because remember the return type is a sequence, so I can call the evaluate method on this and calculate at n minus 1. I could do this, but here I'm just adding it, just writing it down. So basically copy and paste this and just replace n by n minus 1. So n plus 2 becomes n plus 1 minus n plus 1 minus n squared divided by n plus 1 minus 2 n plus n minus 1. All right? This is our Shanks. And we can add more methods for the binomial transformation, Euler's transformation, etc. But these are transformation. How do we use this actually? So let's go back to the PowerPoint here. I have an example here, and it's just from Wikipedia. So I'm going to use a Shanks transform to calculate this series from 0 to infinity, 4 times minus 1 to the k over times 1 over 2k plus 1. And this series turns out to have an exact solution, which is pi. So this is basically one approximation of pi. And this table again is in Wikipedia, you can look it up. But I'm going to plot the sequence. So I define a partial sum, basically from 0 to some n, and call it capital AN. and plot an as a function of n, the index, and also the first shank, and then apply the shank again to the shanks, and then apply the shanks 3 times. All right, and then I'm going to plot the absolute error. So the absolute error for each n is the value minus the exact value, which is pi. So in this case we already have the pi, the exact value, so we can just do a comparison of how applying shanks multiple times actually accelerates the convergence, right? And by that we means that, for example, at after 6 terms, so if I sum 6 terms of this sequence, I get 3.2837, which is far from 3.1415, which is pi. But after transforming using shanks 3 times and then evaluating it at n equals 6, we already at 3.141592, which is very close to pi, right? 5-6 digits of accuracy. So here I have created a test class, test sequence transform. All right, so what I'm doing here in this method, I create the sequence sec, which is k goes to 4 times 1 over 2k plus 1 times minus 1 to the k. So instead of using the power method, I implement this like this. So minus k is equivalent to saying that basically if k is even, this becomes 1. If k is odd, then this becomes minus 1, right? So I have these ternary operations. I calculate the k mod 2, compare it with 0. If it's 0, k is even, so I return 1, and if k is odd, I return minus 1. So this is a much more efficient way. Instead of calculating like math.pov minus 1 to the k, don't do that. Don't calculate minus 1 to the k using that approach. Just call the mod operation. So this is my basic sequence, and what I need, I also define the exact value, which is math.pi, and then I'm going to define my initial partial sum, which is capital AN, and takes n, creates a series class. And remember, series just sums over the terms of this sequence, passing the sequence, and I want to sum from 0 to n, right? So n is a variable, and this basically a lambda expression, and it returns a sequence. All right, so this partial sum is also a sequence. And remember, we want to apply the shanks on this partial sum, not the original sequence. So we create the partial sum, and we want to find the limit of this. But what we find out is that this has a very slow convergence rate, so we have to evaluate it at a very large n, let's say 1000, 2000, or whatever. But now we apply a shanks, so sequence shanks 1. I take the partial sum and call the shanks method, which was a default method. And this is the beauty of the default method, having to add it directly to the sequence interface, because I create the sequence and shanks it, it's another sequence. And then I can call the shanks again on this sequence. I call it shanks 2, twice shanks, and then I take shanks 2, apply the shanks again, I create shanks 3, and all of these are sequences, so I can evaluate it at any n, right? Now I create an array of indices, 20 indices, so I want to evaluate the partial sum at n 0, 1, 2, 3 all the way to, let's say, 19, and then I calculate also the shanks 1, shanks 2, and shanks 3. All right, so my indices actually start from 1, so index 0 is 1, so from 0 to 1, A1, A2, and then shanks 1, shanks 2, shanks 3. And here I'm calculating the absolute error, so evaluate at I minus the exact. Okay, and then what I'm going to do here, and then I create a chart and then plot the index and the partial sum. This is my original slow converging sequence. Color B, shanks 1, shanks 2, shanks 3, and then render plot, marker on, and then x and y axes are both logarithmic because probably the error gets very small, so we want to see on a logarithmic axis, and then I just run. Okay, so one thing here is that there isn't, so if we are plotting on a logarithmic axis, we cannot have 0 as index, so that's why I'm adding index 0 to 1, and then we probably want to also evaluate these at the value of the index, right? So index 0 is 1. All right, so let's run this. All right, that's the result. And let me just add some labels. X label is index number, and then fig dot y label is the Shanks. Shanks 0, 1, 2, and 3. So Shanks 0 is basically the original sequence. All right, and let's see if we can increase the font size. Yes, let's increase the size a little bit more. So we are, as we can see, the blue one is the original sequence, and after 20 terms the error is still pretty big, right? It's between 0.1 and 0.01. So we have to, and it has a very slow converging rate. And then the first shank suddenly reduces the error by more than 1 order of magnitude. After 20 terms, the error is already has like 3 digits accuracy instead of not even 1 decimal accuracy, right? And then the second shank increases again, the takes this first shanks and then shanks it again. So here the error, now the sequence after 20 terms, it has a accuracy of more than 6 decimal places. And then the third shanks basically kills them all. So it has more than 3, 4, 5, 6, 7, 8, 9 to 10 digits decimal places of accuracy. All right, so that's how shanks help to accelerate the sequence. So I'm going to put this here, maybe make it a little bit bigger, and so I hope you enjoyed this video. This is how the acceleration works, and we can use this idea to accelerate any numerical integration method or any type of problem that eventually deals with a series, the calculation of a series. All right, thank you very much. I hope you enjoyed this video, and I'll see you in the next one.